And then if you're ready, I'll just
Yep, that's
so
fine.
I think we're just on 7. So welcome everybody to our final webinar of this season. I'm very, very happy to introduce you to the speaker, Vicente Talanquer from University of Arizona, who of course is a very well known, very well established chemistry educator, science educator. Enormous output in terms of research and interest in terms of learning and teaching chemistry. The way the webinars work for those of you who aren't regular or who are new this time, the audience participation is through the chat text box. So in the bottom right-hand corner of the screen, you'll see a purple arrow, and when you press on that, it'll pop out a chat text box. And you can type in questions or comments there as the webinar is going on. And then we'll have points during the webinar where Vicente will stop, and we'll have some time for discussion. So I will ask your questions to him, and he'll be able to respond to the audience. And I think he's also promising some audience participation at various points as well. So there'll be lots of opportunity, hopefully, for engagement and for chat. We've allocated a slightly longer time for this webinar because I anticipate quite a lot of interest in discussion and as well as celebrate the final webinar of the season. So I'll stop talking and I'll pass you over to Vicente, and we were really looking forward to your talk. Thank you for joining us.
No, thank you, Michael. I really appreciate the opportunity to be here. I confess this is my first webinar, so I'm a little bit nervous of what does it mean to talk to the computer, but I will try my best. I also would appreciate if my voice goes too low, that you let me know, or anyone in the audience lets me know, and also because I tend to have sometimes a thick accent in some words. If you don't understand, just let me know. No hard feelings there. What I would like to do today is kind of tell you a little bit about the work that we have been doing in the, I would say, past 10 to 12 years. Most of my research has been focused on what I would call reasoning in chemistry, but I also have interest in using the results of our research to develop educational approaches that foster what I call, or we have been calling, chemical thinking. It's also important to understand that all of the research that I have done has been done with the students at the college level, mostly at the introductory general chemistry level, that what in the United States is called general chemistry, although we have also investigated progression in understanding through the undergraduate courses. And most of what the work that we do is, in terms of applications in the classroom, involve large number of students in a classroom like the one that you see in the screen. So whatever we design and implement has to be designed to deal with this large number of students. So the way I have organized the presentation today is, again, like in all of the sessions that I have seen in this webinar series, I have two parts. One, I will focus on the presentation of an overview of the investigations that we have done in intuitive reasoning in chemistry, and then describe the types of educational interventions that we have been trying the past few years, with some insights and challenges based on our experience. Given the audience that I can see it's listening to the webinar, it's clear that most of you know that in the past 4 years we have learned a lot about the challenges that the students face to meaningfully understand chemistry. You can see in the screen some of the areas in which we have identified difficulties. I'm not going to be talking about all of them. I'm going to focus my attention on the two areas in which we have developed most of our research that have to do with what I call implicit assumptions about the properties and behaviors of chemical substances and processes, and the other area that is closely related that has to do with heuristic reasoning. So I will be describing some of the work that we have done in those two areas, and also part of how that type of work has informed our changes to our educational practices here at the University of Arizona. for us, or the way we see the challenge in education in chemistry, is that typically there is a huge gap between the way students intuitively think about chemical substances and processes, and by that I mean how they approach explanation, how they build argument, how they make decisions that have to do with the properties and behaviors of substances, and how do we would like them to be to think in our discipline. And the big challenge is, how do you best close the gap, or what can you do in the time that you have available typically in a course to move students from where they are to at least in the direction that you would like them to move. So the approach that we have been following is to try to better understand actually how students think and how they reason. But not only how students think. I have always thought that chemists do not necessarily reflect very carefully in actually how we think as experts in the discipline. What does it mean to use chemical thinking, to reason using chemical concepts and ideas? So we have also tried to characterize what it means to reasoning in the discipline, and then work to design and evaluate educational interventions that can help us move students from where they are to where we would like them to be. So it's also important to highlight, I think, that the way we have approached the investigation of student reasoning has not been traditional, in the sense that we have not been necessarily focused on how students reason about traditional topics or concepts in chemistry. So we don't approach our research trying to figure out how students think about stoichiometry or atomic structure or chemical bonding, etc. So we have tried to identify what we call like core ways of reasoning in the discipline, like a structure property reasoning or causal mechanistic reasoning, and try to figure out what does it mean to think in that way, both from a novice perspective and from an expert perspective, and try to build ways of helping students to move from one to the other. Now, everybody, I think, is now familiar with Johnston's triplet, and we understand the many challenges that students face to connect these three levels of representations or ways of knowing in chemistry. But I would claim that this type of approach, this type of representation sometimes hides the enormous difficulties that are behind trying to move between those three areas. So just to give you an idea, if you want to really move from the symbolic representation of water to explain some of the properties of water, like its high boiling point compared to substances that are similar to water, you really have to be able to manage multiple representations, move between multiple scales, be able to deal with multiple variables, recognize implicit cues in the different types of representations that are used as you move from the symbolic to the macroscopic level, etc. So it's clear that there is a lot of reasoning that the students have to master just to be able to use to interpret the formula of water, and based on that interpretation, make claims about the macroscopic properties of the substance. So understanding those challenges has been part of the research that we have been doing. I don't claim that we fully understand all of the challenges that are involved, but we have been trying to understand some of them. Now, the facts are, at least at my university, is that most of our students struggle to, for example, use structure property reasoning in the ways that we would like them to do. I'm going to show you just typical results that we have gotten working with the students at the University of Arizona at different levels. So this is a typical question that we could use in our research. We identify a set of chemical substances, their symbolic representation, and we want to see how students connect the information that they get through the representations with the potential properties of these materials. So this is a question that we have posed to many students since they start the undergraduate program at the U of A, and also with the graduate students in our university. And so is, for example, ask them to to identify which of these substances could be shiny or malleable. The population of students that you see there are students from starting general chemistry to being above the first year in the graduate school. So the results that you see could be interpreted in some cases as shocking. After 2 years of chemistry at the University of Arizona, 1 year of general chemistry, and 1 year of organic chemistry, students still think that AgCl may be shiny or malleable. And when you do interviews to try to figure out what is going on, it's essentially based on the idea that, well, silver is shiny and malleable, very likely AgCl would have the same properties. And as you can see, it takes over 6 years to get a percentage of the population around 10%. This is not a longitudinal study, this is a cross-sectional study, so it is not clear that the students actually advance. It may be that you just lose the students that from the very beginning were thinking in very naive ways, and you just, the students that only survive are the ones that that have that idea, the chemical thinking ideas from the very beginning. However, this just shows how difficult it is for students to actually build on the type of understandings that we would like them to master. So the question is, why is this one challenging? How are the students thinking? That has been, I think, at the center of my research studies in the past 10 years. And as I said at the beginning, most of that research has been based on the assumption that student thinking is highly influenced by two important factors. One is the assumptions that they make about the nature of the substances and the processes in the world, and also how they go about making decisions of what is important to pay attention to and what to do with what they pay attention to. So I would claim that being guided by assumptions and heuristics is not only something that happens to students, it's a way that humans approach the understanding of their surroundings. So I typically, when I introduce my research, I try to demonstrate that everybody has assumptions that are not necessarily aligned with reality, and that we all use heuristics that help us to reduce the cognitive load of making decisions when we have little information or not so much motivation to complete a task. So in general, the way I define assumptions are implicit beliefs about objects and events. What I would like to demonstrate to you is what could be the type of assumptions I'm talking about. So I assume that everybody is familiar with this dress. So I think that the first question that I would like to pose to the audience is, I don't know if necessarily through the computer this comes across as it should, but Michael, can we start a poll with two options, in which option one would be blue and the other option two would be white? And maybe the audience can tell us how they see the dress, blue or white.
So we have responses coming in now. Number 1 is blue, number 2 is white. So we've about 12 people who are as yet to decide. Any final?
It's fine. I think that gives us a sense that at least we have two types of population. That's good. So it worked. So we have people that may see this as more bluish or more whitish. So in principle, I'm going to try to exaggerate the differences. So people that have analyzed this phenomenon would claim that the difference between the two populations is the type of assumptions that people make about the nature of the lighting that was used to create this photograph. So if you assume that it was natural light, you would see the dress more as blue. And if you assume that it's artificial light, you would see it more as white. So the issue is that you are not explicitly aware of what assumptions your mind is making about the situation. But it seems that the human mind makes a lot of assumptions that are implicit, that both guide but also may constrain the way we think about systems in our surroundings. So again, I'm going to just post you a typical exercise that I always typically post in my talks, just to again demonstrate that we have ways of thinking that, although maybe different in the surface, are relying maybe on the same type of assumptions that we make about the nature of substances and materials in our world. So what I try to represent in the screen is, you have there a ball that is a red ball. The blue screen is just a screen that is going to block your view for some time during the path of the ball. I'm going to try to simulate the behavior of the ball with different slides, because the system doesn't allow us to use animations. So I'm going to try to do my best to try to represent this experiment. And then what I would like you to do is to think about what is happening in this system as you see whatever you see on the screen. So I'm going to start the experiment now. The ball is going to move slowly. As you see, it's blocked by the screen. And there you have it. That's the phenomenon that I would like you to reflect about. So I'm going to go back to repeat it. And I'm going to ask some of you, whoever is brave and a fast typer, maybe to let us know, what do you think is going on? So what is going on here? How would you explain what you see? So we have one answer that says that maybe one ball pushed another ball behind the screen, collisions between two balls. So that seems to be in the same direction. So it seems that everybody agrees on more or less the same, that there's a larger ball hitting a smaller ball. So another interpretation is that the screen moves away, so the same ball looks smaller, so we have an issue of perspective. So what I could claim now, that is, this is fine. I ask you a question, you give me some answers, and I can tell you that everybody has a misconception. Why is that? Well, because I'm the one that gives the answer to the question, and you just try to come up with some answer on the spot based on, I would claim, assumptions that you made about the nature of the system you are dealing with. So when I presented this to you, I immediately biased your thinking when I said that that was a ball. So I didn't say that's an electron. No, that could have changed the way you think about what is going on here. I said this is a ball, so I immediately primed you to think about, what do you know about the behavior of balls? So in principle, you don't expect, for example, balls to suddenly shrink and become smaller. So no one here claimed that what happened is just that the ball spontaneously shrink behind the screen. So that is not something that we're expecting to happen. So in general, people have done a lot of research with kids, with infants, about how they look at this type of phenomena, and they have found that most of us have certain assumptions about how solid objects behave. We assume that they are going to move in continuous trajectories, that they are going to move in coherent trajectories. That means they are not going to break apart, and that they are going to persist over time and space. So those are the kinds of things that I call implicit assumptions. These are things that we assume about the entities we are working with, but we are not necessarily aware of those assumptions while we are asked to build explanations about a phenomenon. Also, you can claim that now you are aware of them, but you were not necessarily aware of them while you were trying to generate an answer to the question that I posed. So the reality is that when we are confronted in science classes with questions for which we don't necessarily know an answer, and I'm just presenting to you some of those questions in the screen from different areas, not necessarily just for chemistry. The reality is that when you pose those type of questions to people, most people will generate what we would call the incorrect scientific answer, because the assumptions that we make about the behavior of birds or flowers do not necessarily apply to these situations. So we make assumptions that are not necessarily appropriate for the type of systems that we are facing or confronted with. So we have, over the past, again, 10 years, trying to figure out what are these assumptions that students, and I would claim in general people, make about chemical substances and phenomena. We have labeled those assumptions in using what I would call sometimes weird names. Just find a word that is trying to represent a way of thinking is not always easy. But those words like additivity or inherence or homogeneity, are they just trying to represent a way of thinking or an assumption that we have found that is quite pervasive in our students at the college level, and that has a quite strong influence in the way they think about chemical substances and processes. So I just would like to illustrate to you some of those assumptions that you can call intuitive assumptions or implicit assumptions that people do, that people make about substances. These are the typical type of questions that we have used in our research. We typically do research by both doing individual interviews in which we pose these type of questions to students and we ask them to think aloud and tell us what they think and try to figure out how they are reasoning. And we are also do surveys that we apply to a larger number of students just to get a sense of what are the trends and if in some cases if the hypotheses that we have are in line with what we find after the students complete the surveys or the questionnaires. So this is a typical question in which we are trying to explore how students connect information that they receive about the properties of substances to try to make predictions about the properties of the products that these substances may generate when they react with each other. In this particular case, the students were asked to predict the color of the product of a chemical reaction of a substance that had a blue color and a substance that had a yellow color. And again, we have asked this question to many students at different levels of preparation in chemistry. And when we ask these questions, we typically have in mind the type of assumption we are trying to explore or to see if the students are using to generate the answers. In this case, we were trying to test if the students were relying on what we call an additivity assumption. That is the idea that essentially the properties of substances, the macroscopic properties of substances that we observe are typically the average of the properties of their components. So that is just we call it additivity because essentially they are just adding or averaging the properties of the components without necessarily understanding that in many cases the properties that we observe emerge from the interactions of the particles and are impossible to predict if you don't have the right information that in this case is not provided to the students. So as you may expect, many students think that they can actually predict the color and that the color would be green. That would be the kind of the intuitive assumptions that you would make if you think of blue and yellow as just two colors that are combined. And as you can see, our students, at least at the University of Arizona, after 1 year of Gen Chem and after 1 year so essentially after 1 year of Gen Chem, they have not changed much in their beliefs about the ability to predict the properties of substances just by combining additively the properties of their components. And then again, you see this pattern that over the years, students may be able to overcome this assumption, but it takes a considerable amount of time. Now, we have also explored other type of assumptions that we call, for example, centralized causality. This has to do with the idea that we tend to think in general that when there is an event or a process, there is always an active agent that acts on more passive agents to produce some type of change. So the type of questions that we have been posing in this area are questions like, for example, you have a chemical reaction between two substances. One of the substances is more has more of some properties. So for example, you could say A is more polar or A is more electronegative. Whatever is just giving A some priority over B. And then you ask the students which one of these substances will start the reaction. And you can again predict that a significant number of the population of the students, and in this case, independently of the level of preparation, are just, I would say, tricked or guided by their intuition. I will talk later about whether these type of results are actual manifestation of what the students know and the type of reasoning that are capable of doing, but at least these results are indicative of what is their spontaneous answer when they are not thinking very deeply about the question, or they are just providing the first gut answer to the questions that are being posed. So in some cases, we have found, as I will show later, that students are unable to control their intuition and that experts are just better at doing so. And so it's not necessarily that these answers reflect the actual understanding of the students, but they are, I would say, distracted by or influenced by the specific nature of the questions that we pose and the information, the surface information that they extract from the questions that are being posed. So another assumption has to do with the not only how reactions happen, but why do they happen. Again, you can ask a question like, you have a oxidation reduction reaction, electrons are transferred between the species. Why is that this transfer occurs? And you can give different options, like it happens because one of the species attacks the other one, or you can just say that it happens because the substances want to become more stable. That's what we call the teleological answer. And what you find is that that answer is quite attractive, again, to many students across educational levels. So I'm not claiming that this is the only type of reasoning that the students could be able to express if pressed to provide a more in-depth answer. I'm just claiming that intuition is very difficult to control if you are not an expert or if you are not metacognitive about your own reasoning. So what we have found is that these type of assumptions actually have an influence and a strong influence in the way our students think. So in this image, in this slide, what I'm trying to represent is we have this set of assumptions that are kind of underlying the reasoning of the students. Then they receive these pieces of information in our classes that I'm representing with the Lego pieces. And then they put these Lego pieces together, guided by the underlying assumptions, and then they build these hybrid monsters that are the type of understandings that they manifest in our exams or in our research interviews. So these are hybrids of pieces of knowledge that they are receiving in the classroom that are assembled using assumptions that are not necessarily the assumptions that actually guide chemical thinking. So this kind of summarizes the part that has to do with assumptions. Michael, I don't know if this would be a good moment just to have a brief break, just because I also don't like to talk for a long period of times. So maybe this would be a good time to stop first.
Great. Yes. So if you have any questions, feel free to type them in. One that's come in already is. You mentioned a little bit about how questions are phrased, but how much do you think about how questions are phrased affects students' intuitive responses? So the question specifically is, if you rephrase the question, do you think the response would change? This was to do with the, I think it wasn't additivity, it was the one after additivity. Yeah.
So I think that I can see that students are fooled by the language, but what I'm saying is that they would be fooled by any language. So that is unavoidable that we use the information that we receive in the form of a question, and we interpret that information based on what we know, and what we know is both explicit and implicit. So what I'm talking about here is that there are implicit pieces of knowledge that are going to fool us if they are deployed in the inappropriate context. So that becoming an expert sometimes is just learning to identify in which context to apply specific assumptions. So is that students already may have the expert assumptions, is that sometimes they don't know what context they should be applied to.
So in relation to that, Maria, is just a nice follow-on. Do you make them aware of this, and does that change their behavior then?
So what I'm going to do with that is I'm not going to answer right now, because I'm going to show results later that answer that question.
Alison,
yeah, the answer was...
Sorry, yes. Yeah.
Okay. Go ahead. Yes.
Thank you. Alison's asked, can you give a little bit more about the instructional context? Do students learn about heuristics or whatever in these settings?
Well, first, I wouldn't say that my students learn about heuristics, the type of heuristics I will be talking about in the educational context. I think that the heuristics I'm talking about are heuristics that humans develop through their interaction with life. And also maybe some people would claim that some heuristics are even innate, that we come wired with some of them. So, but without getting into that debate, what I'm not talking about things that are necessarily developed in the classroom, although I think that some of our instructional decisions may reinforce certain assumptions and certain heuristics. But I also believe that really educators are not that bad. So we don't do so many bad things to students. Is that the human mind has already some ways of thinking, and then we just sometimes reinforce ways of thinking that are not very productive in a particular context or not.
Great. And Renee asks about following up on these questions with interviews. Do you have any sense about why students are choosing particular answers apart from just the assumption of a particular intuition?
Yeah, so in most of our research, the research involves interviews with the students. And in most cases, what we have found is that actually students, I would say you have a variety of things because the students are different. But in some cases, you find the students that make assumptions, and those are the only assumptions that they know how to make. So that means that they have not developed alternative ways of thinking that they can pull from. So teleology is a typical case. So the typical example in teleological thinking chemistry is asking the students why the atoms want to have 8 electrons in their shell. So this idea of atoms wanting to behave in a certain way is very strong in our students. And the fact is that many students cannot go beyond of that assumption because they have not developed an alternative assumption that is not based on some kind of desire to gain stability. So in some cases, that is the problem. Students actually don't have alternative assumptions. And in other cases, what we have seen is that students have developed other assumptions, but they do not deploy them with the same facility than they deploy the intuitive assumptions. They need to be prompted. They need to be pressed to think about them, to deploy them in an appropriate manner. So those are the two types of things that we have observed in interviews.
Okay, there are some more questions coming in, but I'll keep note of them now, but perhaps we'll continue with the seminar.
Yeah, so I just would like to address one of the questions that has to repeat 2 times, that it has to do with P, in fact 3 times, that has to do with P prims, and I think that that's an important question to address, because I think that I have to make a stand. I have to be more upfront of my philosophical stance here. That is, I I think that most of the research that we have done is pretty well aligned with Dissesa's ideas of phenomenological primitives or primitives. This idea that students have fragmented pieces of knowledge that they deploy in particular situations, and you cannot say that they are wrong or right. Simply you can say that they are deployed in appropriate context, maybe, and that they may lead to misconceptions. So I think that assumptions can be thought as p-primes. However, that's the part that for me is important. However, there's a however. I think that the p-primes is too fragmented. I think that the research that we have done shows that there is, for example, when you think about causality, students do not have only pieces about causality. They have very well developed ideas about how causal behavior happens. So it's not that you just think that the more strong is an agent, the more active it will be. That is only a piece of what they think. Not typically they think that agent has intentions, that those intentions have to do with getting to a better place in life, also to be more stable, to be happier. So I think that those p-primes are not as disconnected and fragmented in many cases as represented in Dissesa's framework. So I refrain from calling them p-primes because I think that in some cases it can be very fragmented, but in the cases that we have investigated, those fragments are more connected than what the p-primes framework seem to imply. Do I move forward now?
Sorry, my microphone was off. So, yep, yes, please do. I think continue. Thank you very much for that answer. And Elena, I'll let you follow up on that if you want to, and we can pick it up later on. So, yes, please do continue.
Very good. So the other part that we have done research has to do with heuristics. Heuristics are more associated, not necessarily with the assumptions that we make, are more related to the type of reasoning strategies that we use to make decisions and build inferences. Again, I'm going to try to demonstrate that you or any human being relies on heuristics to make decisions. So I'm going to show you in the next slide, I'm going to show you images of two types of milk. I imagine you go to the supermarket and you have two options. So I'm going to ask you to, and Michael, maybe we can do just a poll. Again, it's for two options that I want you to choose one of the milks. Which one would you buy? And I don't want you to think very carefully about it. I just want you to use your gut reaction of which of those two milks would you buy. So these are your two options. And let's say the one is latte, the other one is accurate. So could you tell us which one would you buy? Maybe latte is 1 and the other one is 2. Okay, I think that even without the poll, it's clear that the majority of the people responding have a preference for latte. And then I would ask you, it's just a rhetorical question to think about why do you choose latte when you don't have a clue of what latte is or not, or what is the difference between the two milks? What is the difference between milk? But the reality is that you can predict that most of the people are going to choose one over the other. The same way I could pose you the questions, who of these two people would you trust? And I also can predict which one which one would you choose? So the question is, why is that we are able to make these decisions with the information that is available? And in some cases, these decisions are right on the spot, or are the most productive decisions, and sometimes they are not. So part of the research that we have done is to try to figure out to what extent these type of heuristics affect the decisions that our students are making when they are confronted with chemical problems. That is, we wanted to figure out if our students were relying on this type of heuristics to make decisions rather than relying on their chemical knowledge and chemical thinking. So again, I'm going to present in the screen some of the type of questions that we use in our research. Typically, when we do this research, we give students choices, or we ask them to rank substances, things that imply that they have to make some type of decision. And in this case, for example, we told them that we wanted to design a CAM burner, that they had two options as fuels. One was CH4 and the other one was CH4O. And that's how the information was presented to them. In other cases, we have presented the options as natural gas and methanol, because that may change the choices that they make. So in general, what we found is that most of our students in general chemistry, no matter when in the semester, they tend to strongly rely on heuristic reasoning versus chemical thinking to make their initial decisions. And the way this works, I'm going to try to generalize the way the students are thinking when using this type of heuristics is the following. So they typically, and that also happens to us when we make decisions, we focus on the most salient differentiating features between the options that we are given. So in this case, for example, the options that we are given CH4 and CH4O, the most differentiating feature is that one of the entities has an O and the other one doesn't has it. So then, if possible, we associate that differentiating feature with the targeted quantity that we are trying to evaluate. So for example, in this case, we are trying to figure out what would be the best fuel. So that's our target quantity. And then we try to associate the difference with the target quantity. So our mind starts trying to figure out, okay, how is all connected to fuel? And don't make, so that's when implicit assumptions or implicit or explicit knowledge comes into play, because then we may say, oh, what do I know about oxygen? I know that oxygen is related to combustion. So maybe having a lot of oxygen is good for combustion. So, well, let me choose CH4O as my option because it has more O, and that means it's better for combustion. So essentially what happens is that by doing this type of associations, we substitute a difficult question with an easier one. So the difficult question is which one is actually the best fuel, and that would imply thinking about many variables, from heats of combustions to a state of matter, etc. And we simplify the things to just a single feature that is very salient that somehow we associate with a targeted quantity. So instead of answering the question, which one is the best fuel, the question that we answer is which one has more oxygen. So we have tried to explore to what extent our students rely in this type of reasoning in our classes, and we have identified limited of the very pervasive heuristics that the students use to make decisions. We call one of them recognition, another similarity, and the other one is one reason decision making. So I just would like to illustrate how they may work in a chemistry setting. So for example, typical questions in chemistry when you are dealing with having students to connect a structure to properties is to rank, for example, acids from stronger to weaker. It's a typical question that you could see in a general chemistry curriculum. And what we have found is that these are our two most common rankings. Also, in one of them, HCl is identified as the strongest acid, and the other one is H2S as the one identified as the strongest acid. None of them is the chemically correct based on the analysis of the actual structure of these substances. But when you do interviews, you find that the students essentially rely on heuristics to make the decision. So for example, in the case of this ranking, what they would say is that, well, I know that hydrochloric acid is a strong acid because I have used it in the lab. So they recognize the entity as a strong acid. They use that as kind of an anchor to start their ranking. And then they use similarity to make their decisions. So they say, okay, so HBr looks like HCl in kind of in the formula, so very likely it's the next one. And then H2S is just too different. Very likely that is the weakest one. So that would be a typical way of reasoning to justify this one. In this case, you could say a student that doesn't recognize HCl as a strong acid, but what they recognize or they remember is that acids have something to do with H's. So, well, maybe H2S that has more H's is the strongest acid. So they choose that. Then they may go with recognition for HCl and then with similarity for HBr. So essentially, there is this simplification using surface features to make decisions, and recognition and use of prior knowledge and some implicit assumptions to then justify whatever decisions are made. So we have seen this pervasively in our students. We have identified different type of assumptions and heuristics that they use. And what we have found is that there is a significant difference between the type of thinking that they manifest and the type of reasoning that we would like them to develop in our classrooms. So that has posed a major challenge to us and has opened the question of how do you help students close the gap? How do you move them from where they are to closer to where they want them to be? So we have been trying a variety of things. I'm going to describe to you some of the general things that we have tried to do and some of the more specific things that we have tried to do, and our successes and failures or challenges that we are still facing. So one of the things that we decided to do based on the results of our research is that we thought that we had to do something about the way we were teaching our students chemistry. Now, we had the ability to make changes in general chemistry, so that's where we started with our modifications. And we did modifications at two levels. One is try to rethink actually the curriculum to modify them in such a way that we thought was better aligned with developing ways of thinking in chemistry. And then we also decided to modify instruction that was better aligned with evidence-based teaching practices, but also with the nature of our curriculum. So we have worked in trying to modify both how we are engaging students with the content and how both in sense of curricular decisions and instructional decisions. So in terms of curriculum, what we have done is to try to identify ways of reasoning that we value, that our students develop. Again, I will insist that the population of students that we work are college level students. And so we actually want them to develop some particular ways of reasoning that we think that are valuable, not only in chemistry, but in other science and engineering areas. So we have emphasized a curriculum in which the students spend a lot of time thinking about a structure-property relationship and also about mechanistic reasoning and how those two types of reasoning are useful to make decisions and to move to solve problems in critical areas in chemistry, such as characterizing substances, making predictions about the directionality of reactions, etc. So that has implied a dramatic change in the way we engage students with the content. So we do not engage students from a topical perspective that is very common or conventional in general chemistry. So we don't confront the students with, today we are going to talk about stoichiometry or atomic structure. We have reorganized the curriculum around what we call core disciplinary practices. So it's more about how do you go about analyzing substances, determining structure, harnessing energy, controlling reactions, etc. So we are kind of moving away from a topical approach to a more practice-based approach. And I'm using the term practice in the same way that in the United States, the next generation standards talks about science practices, but this you can see it as more chemistry-specific practices. And so we have transformed the curriculum. We have developed our own instructional materials. So this is the typical coverage of our Gen Chem curriculum, in which now the units of instruction are centered around questions that are reflective of these different practices that we call core disciplinary practices. If you are interested in learning more about the type of curriculum that we are using, here you have an internet link that you can follow later, and then you can see the materials that we have developed. We have many materials available in the internet, so that can give you a good sense of how we are approaching the curriculum. The other thing that we have done is to think very carefully about how to help the students progress in their understanding. So the way we introduce ideas and concepts and models in the curriculum has been carefully thought out, so that we engage first students with reasoning at the macroscopic level, using mostly experimental data to try to make sense of what is going on. Then we introduce the idea of modeling with a very simple particular model of matter, so that they get a sense of what you can do with a model of matter that is pretty simple, but is actually very powerful in making sense of data, particularly physical data about the properties of substances. And then we move to engage students with the analysis of more sophisticated models of matter that go into the molecular or the more electronic levels. Again, with the idea that always you have to look at data to make sense of why these models are more productive or useful in certain situations. So as I said, we have also modified our instruction. We are trying to follow as much as we can the idea of a learning cycle. We tend to guide our instruction always by using an anchoring problem of phenomenon that is kind of the center of our discussions. And then we engage students in exploring, constructing ideas and applying those ideas in different settings. So a lot of the things that, because we want to emphasize chemical ways of reasoning, a lot of what we have been doing is to try to engage students in data analysis, and based on the data and the analysis of data, generate models, engage in argumentation, and then use those models to make predictions that may be corroborated with additional data. So this type of cycle of data analysis, modeling, argumentation, prediction, going back to data is very typical in the way we work with the students in the classroom. So we have developing, because modeling has become a critical piece of what we emphasize. Why? Because we believe that it's through the engagement with models that you actually develop the type of reasoning and the switch in the type of assumptions that you have to make to build explanations. So our bet at this moment is that by creating more modeling resources, engaging students in more modeling opportunities in the classroom and outside the classroom, we will have some impact on the type of assumptions they make and the type of reasoning strategies that they use to make decisions. We have also changed the nature of the classrooms in which we work. We typically work in these lecture halls with thousands of students facing to a board. Now we're trying to move to these more open spaces where students are sitting in small tables. You can see here one of our larger collaborative learning spaces hosts 250 students. So we are also trying to change the physical setting to emphasize this importance of engaging in discussion and reasoning and modeling in a collaborative manner, and to able to make, most than everything, to make a student thinking more visible to the instructors in the classroom. And I call instructors because there is more than one instructor there. You have an instructor, a leading instructor, but we have, in a room like this, we will have between 15 to 20 learning assistants working with that instructor to support a student in the classroom. We have also tried to modify the way we do assessment. I think that it would be not very successful to try to modify curriculum without to look at the assessments that we use. there are two main things that we are trying to change with our assessments. So we are assessing in context. That means is that whenever we pose questions to students, they are in a realistic context for which we have data that can be analyzed or can be studied. The data can be qualitative or quantitative, but there is a context with data in which the data has to be modeled, explained, argue about with, etc. So that's something that is a critical piece of the assessments that we are developing. Again, if you want to see these assessments, they are available online in the same website. And what we are also doing is to develop assessments that more critically look at reasoning. So we are not only paying attention to whether the questions that we are posing are kind of pressing our students to move between the symbolic, the macro, and the microscopic level. We are also paying attention to what type of model of reasoning are we expecting? Are we expecting just an association, what we call relational reasoning? Are we looking for more a mechanistic explanation? So we are trying to look very specifically for the type of reasoning and also for the type of rationals that we want the students to build. I will claim that in chemistry, we are not only dealing with macro, submicro, and symbolic, we are dealing with many different ways of explaining stuff. Sometimes we use a phenomenological approach in which we want just the students to use macro concepts to explain a phenomenon. Sometimes we use a mechanical approach and we want them to think about particles interacting with each other. And sometimes we want them to look at the structure and use the structure and composition information to make claims. So we are also trying to figure out what type of rationals we want them to be able to build. After all these changes, so I think that you have to wonder, are we being successful or not? And the answer is, well, maybe. So the fact is that we have developed a variety of instruments that we are using right now to explore student reasoning. So for example, we developed what I call an intuitive chemistry inventory that tracks this type of assumptions I talked about at the beginning, in the first part of the talk. Again, if you want to see the questionnaire, just to get a sense of the type of questions that we are using to assess, you can see it here, and you can also complete it if you're interested in complete it. It's a 20 multiple choice questions assessment. And what we do is we apply this in a post, and a pre and a post format in our classes at the beginning of the general chemistry sequence and at the end. And the IC is is doing online. It's an online assessment. And these are the type of results that you see in a pre-post assessment. This is separated in different areas that are associated with different type of assumptions that we target, that we want to see the students grow. You can see that the pre-average is in their 30s, the post-average is in the 45%. So that means there is improvement, but this improvement is not that great as great as we would like, given the type of interventions that we are imposing in the classroom. So there is a challenge there. So I just wanted to be very honest about the level of success that we are having. And as you can see, we have great success in some areas and not much success in other areas, no matter how much we are insisting in these ideas of developing some other types of mechanistic or causal reasoning. Now, when this is a comparison between the beginning and the end of our courses, this is a comparison with before we changed to what we call the chemical thinking curriculum. We collected data prior to the change in the curriculum. And as you can see, the chemical thinking change has had an impact compared to what we were doing in the past. But again, we are talking a change between a 30 and a 40% in students' performance. So based on these results, one of the questions that we had was, okay, is this type of questionnaires giving us actual information about what the students are capable of doing it? Or they are actually just telling us how much they are still guided or controlled by the intuitive reasoning. So we did an experiment. I would claim a very simple experiment. We wanted to see if students would improve their performance if we somehow prompted them to control their intuition. So what we did is we took the same questionnaire, the intuitive concept, the intuitive chemistry inventory. We asked a set of students to answer that questionnaire as it was, and another set of students, we asked them to complete a questionnaire that was a slightly modified version. It has the same questions, but each question had another associated question that said something like this. It provided the same options that the question before, but the students had to select the option that they thought was chosen by students who got the question wrong because they did not carefully reflect on what the question was asking and were misguided by their intuition. So we were asking the students, please just select the option that you think a student that is guided by intuition would have selected. So we thought that this additional prompt may prompt the students to be more metacognitive about their answer, at least to reflect on the answer that they had provided. And what we found is that we were correct in a variety, and the effect was not small. This is a graph that shows you the performance of the students. In blue dots, those are the performance of the students that just did the traditional IC. In red, you can see the performance of the students that completed the IC with this additional metacognitive question. And we divided the students based on their performance in the final exam, that is a standardized American Chemical Society exam. And what you can see is that all groups of students, from underperforming to the students that get A's and B in the class, all of them benefited by at least 10% in the score by just being prompted to reflect on the answer that they had provided. Now, when we analyzed this by assumptions, what we found is that they had improved, they had large improvements in some type of assumptions, like, for example, at the additivity assumption, but not so much in other assumptions, like, for example, the way they thought about how the properties of matter at the submicroscopic level compared to the properties at the macroscopic level. So it seems that this reflection may help them in some areas, but not necessarily in all areas that we were targeting. So I hope that that gives you a sense of the type of research and that we do, and also the educational development in which we are engaged. For me, this was a great opportunity just to communicate the two areas that we have worked with. These are the people that have been involved in the research that I presented over the years, and are also the instructors that are trying to figure out how to improve student understanding at the University of Arizona. And if you have any questions, of course, I will be happy to answer them here, but you also can contact me via email, and my websites are also on the slide. Thank you.
Wow, thank you very much, Vicente. That was quite a sweep of an enormous amount of work. So thank you very much. The questions have been coming in thick and fast, so I will do my best to represent the questioners. But I've just said to them that if I don't ask a question and they're particularly keen, for them to repost it, and I'll make sure I pick it up. A couple of practical issues first. You mentioned a little bit about changing assessment, but obviously, if you're changing your teaching approach, is your overall assessment process changing as a result of your new teaching approaches?
To some extent. So I have to acknowledge the realities of the classroom. Or now we are dealing with sections with 250 students. So what you can do with that in that setting is always constrained. So we have been trying to increase the amount of formative assessment that we do in the classroom. So that is a change in terms of assessment. It's not only changing the summative, but also the formative assessment. So for that, we are using a variety of online systems that allow us to collect student data in real time. No, they can make graphs or make plots, and then we can collect that and immediately display that in the classroom. So, and we can collect that. So we are collecting more data, and with that data, we are, to the extent that is possible, to try to make decisions about what to do the next time that we meet with the students. In terms of summative assessment, I think that we're still very traditional in the way they are deployed. We have 5 summative assessments throughout the semester. Now, the way what is maybe innovative is the nature of the assessments. Those assessments are context-based, are much more carefully designing what the questions are asked, but they are deployed in very traditional ways.
Staying on a practical level, I think there was this kind of a slight gasp around the world when you said 15 to 20 learning assistants. So there's a couple of questions related to that. In terms of buy-in from your colleagues and in terms of other people involved in the general chemistry course, how did that kind of process work out? What kind of training do you give learning assistants in their dealings with this kind of new scenario?
Yeah, so the learning assistants are at my institution are undergraduate students that have successfully completed the courses. They have earned an A or a B, and they enroll in a course for credit that is called, we call it a preceptorship course. So they don't earn money. We don't pay for their participation. They earn credit for their assistance. And then they get trained through our weekly workshops. So they meet once a week with a trainer that is one of the instructors of the course, in which we, as much as possible, and again, I don't want to lie because I don't want to create this idea that, wow, everything is perfect. It's not. No, I mean, we have to struggle with these learning assistants that have been in the course. They have the advantage that they have a sense of how we engage the students in discussions and the importance of collaborative work. But even with that, they have their own assumptions about what good teaching looks like. So we have to work very carefully with them, but still we have a range of performances in this group of instructors.
Yeah. When you were talking about the pre-post, and there were some improvements and some not, and John makes the comment that, you know, what's been done traditionally, of course, has been refined to almost perfection, and now you're changing something, and there's probably still scope for refining. So do you see over the coming years, perhaps as this model settles down and becomes more refined, that you may see improvements on the pre-post? I hope I've reflected your question there properly, John.
I hope so. Again, the realities of implementation are sometimes tough to deal with. You know, is that I said we have to implement this in courses with 250 students, and we have several sections of this. So they are taught by a variety of instructors. So we are working with maybe every semester 6 to 8 different instructors teaching these sections. And so we also have to deal with the reality that different instructors implement these things in different ways, and not all of them are equally effective in their implementation. So what we are doing right now as another intervention is to work with instructors to figure out via co-teaching or peer observations, how can we improve the implementation of in the classroom, and see if that has an impact also on the student learning.
There's a couple of questions then about the methods and some of the later data you presented. We were just wondering about I suppose the ICI instrument itself. Was that related to the paper you mentioned that's under review, or where would people find out a little bit more about that?
Well, the paper that I mentioned is already published. As they can see there, the same results that I just presented here is just published this year in Journal of Chemical Education. So if you want the questionnaire, you can just email me and I can send it to you, or you can see it online on your own. The IC questions come from different sources. They come from already concept inventories that were developed by other people and validated by other people, or they come from research that we have done, questions that we have tested through our own research. Now, the instrument as a whole has not been validated in the way that an instrument should be validated. So the way it works is that it provides to us information about the answers to questions that we typically have seen patterns of behavior that are indicative of the assumptions that we are looking for. But as an instrument, I'm not going to put my hands in the fire in terms of saying, oh, this is a validated instrument.
Yeah. One Question. I mean, obviously, you gave the context very clearly at the start about teaching general chemistry students at university level. These findings about reasoning that you're seeing, how do you feel they may translate to younger age groups? And do you have any advice for teachers of those age groups?
Okay. I think that they translate almost directly. I have to be, I believe that I have worked with some secondary school students. We have seen the same patterns there, but also there's a lot of research literature out there on the secondary school level that is very in line with the type of things that we see at the college level. Also, for the audience that are not from the United States, I mean, I'm originally from Mexico, so I can tell you that what we call general chemistry at the United States, it may be what you call high school chemistry in many countries. You know, so the similarities of the content and the maturity and the level of the students is very similar to what in many other countries would be the high school chemistry level.
Okay, yeah. There was one other. Oh yes, when you were talking about models, you mentioned the idea of the importance of modeling and building modeling. How do students understand the limitations of a yet more advanced model? In other words, do they understand that each model is a successive, slightly better guess of what's going on?
I don't think that we have assessed or evaluated to what extent our students' understanding of modeling is improving. So this has to do more with their epistemological knowledge or not, is to what extent are they being able to recognize what a model is and how models are evaluated and refined. So we have not done any evaluation that has to do with observing changes in their epistemological beliefs. The only thing that we have done at this moment is to create a learning environment in which revision of models is explicit and pervasive. So that means that we are very explicit on the fact that we are working with the students with a model that explains certain facts or certain data that we are providing, and then we introduce new data that model does not necessarily is able to reproduce, and then we very explicitly discuss how the models have to be revised or could be revised or experts have revised to try to deal with it. So at this moment, I don't have answer in terms of success. I just have good intentions, I guess.
Anna asks, I think I'm not sure whether you addressed it. The 5 assessments you mentioned in the redesigned course multiple choice. Sorry, are the 5 assessments you mentioned in the redesigned course multiple choice, short answer, or a combination?
It's a combination. Again, given the nature of our program with so many students, we have to settle on a combination that is feasible, in terms of grading. So typically it's a combination of multiple choice tests, multiple choice questions, and open response questions.
Okay. And Rene asked about the paired questions. Could students change their initial response having seen the paired question?
Yeah, they had their ability to see all the responses and change them. Now that's an excellent question, because the questionnaire was done online, so we have not yet done interviews with students to see how they actually work through the questions and how much they go back and how much they change. No, we just know that they change. We don't know how they go about the changing. So that's a black box for us at this moment.
Okay, I think we have certainly got our value for money from you, Vicente. Thank you so much for sharing your expertise, and your just the scope of your research is just really inspiring. So thank you very much. And as I mentioned, you have finished our webinar series, and I have remembered to press record on all of the webinars, so they are available on our YouTube channel. That is accessible through the website, and a really great scope of research has been shared with us from a range of international experts around the world. For those of you who have withdrawal symptoms over the summer while our webinar series is on break, we had Jack Barbera at Edinburgh this week, and I recorded his webinar that was about looking at flipped learning and studying flipped learning in chemistry. So that is available if people want to view it as well. But I think we'll just have a kind of a virtual round of applause, Vicente, for such an amazing talk. Thank you very much for sharing your work and expertise with us. I'll try and copy the chat transcript so that you have time to go over it. I'll email it to you so you have time to go over it at your leisure. But thank you very much, and I will stop recording the webinar now and officially close it. So thank you very much for your time.
Thanks.